Hey, how you doing? Good evening. Yeah, good evening for me right now. Well, it's about 5:25. It's good to see you. This is going to be pretty short, sweet. I say that all the time, don't I? Let me go ahead and share my screen, okay? This is going to be about atoms and more so about isotopes. So not really so much just atoms. Like I said, let me get my screen sharing going on here. So actually this is more about isotopes. And what you want to realize is that most atoms, elements on the periodic table have, I call them like brothers and sisters, they're isotopes of the same element, okay? So I'm gonna go here, I'm gonna go here, I was not prepared, go here, and we will add, oh, I'm not sharing. Let me try that one more time. Screen, zoom. Okay, here we go. Okay. Come on. And we're going to go here. Okay. And this is going to be, as Ms. Murphy said, isotopes. So I'm just waiting for my MacBook. There we go. Let me fix that. I'm very particular about my pen size. So I'm going to take it down and choose a different color. Isotopes. All right. Okay. Same element. Because it's the same element, it has the same number of protons, right? You can't be the same element and not have the same number of protons. What it is different though, is they've got different mass numbers. Right, different mass numbers. Actually, I did not mean to say that. They've got different numbers of neutrons because, let me clean that up. Oh, goodness gracious. Because they have different numbers of neutrons, they also have different mass numbers, okay? Because if you recall, right, we know that the mass is composed of the protons plus the neutrons. And all the mass is of the atom is in the nucleus, and that's the sum of the number of protons plus the neutrons. So if we start changing numbers of neutrons in an atom, we also will be changing the mass number, okay? So what we see is we can look at this 3 different ways. For example, or a few different ways. Carbon has 3 naturally occurring isotopes, okay? Carbon has 3 naturally occurring isotopes. We've got carbon 12, we've got carbon 13, we've got carbon 14. So what we have here are 3 carbon atoms. They're all carbons. This number here is your mass number. All right. This number here is your mass number. And this number here is your mass number. Anytime you have an element symbol dash a number, the number is the mass number. Okay. It's not going to be the number of protons, the number of neutrons, the number of electrons. It is the mass of that atom. Okay, well, this is carbon, so it's got 6, oops, let's just make that a 6. It's got 6 protons, and then 12 minus 6 equals 6 neutrons, right? Because the mass minus the protons equals the neutrons, right? So if you don't know how to get neutrons, mass number minus protons equals neutrons. Okay, every time. This is carbon, therefore it has 6 protons. Anything that's carbon has 6 protons, and anything with 6 protons is carbon. However, 13 minus 6 gives us 7 neutrons. And you can already see here, this is carbon, it's got 6 protons, oops. and 14 minus 6 gives us 8 neutrons. So these are our isotopes of carbon, and they differ in their numbers of neutrons. Because their neutrons differ, their mass number differs. Okay? Okay. Now, there is something called oops, don't want that big old guy. There's something called isotopic notation. Okay? And the way I believe it should be done, and if you see it opposite, just accept it. But this is the way Miss Murphy wants you to do it. Okay? Element symbol, right? So that's the element symbol. And we'll put a number on the top. We actually call this number A. Okay? We're going to put a Z on the bottom. The number on the top, little superscript up top, will be the mass number. And the number on the bottom will be the atomic number. Okay? And you need to recognize if you see something as such, that's what's going on. Now, sometimes I see in certain places where these numbers are actually flipped. But when you write it, I want you to do it like that. Okay? I think that's best. Now, so if we were to take our carbon 12, carbon 13, and carbon 14 isotopes, right? We would see that we could write this as C12,6, C13,6, C14,6. Okay, so it's two kind of different ways to represent the different isotopes. You need to recognize both. I have a feeling that something you're going to see is going to go like this. And I don't want you to worry too much about it, but I personally think that that is the way it should be done. Okay? Write questions down if you have them. If there's something you don't understand and would like for me to explain, please ask. Now, I think it is important to realize, once again, these are mass numbers. Okay? Now, if we were to look at carbon on the periodic table, we would see this. Right? This is not a mass number. Okay, this is actually called something different. This is called the average atomic mass. Okay? Now, some of you might be asking a good question to yourselves. Well, what is it the average of? Because please notice, it is not the average of this, this, and this, because that average would be 13. This average is 12.011, so it is a special type of average. Okay, some of you aren't going to hear me, and you're going to mess this problem up time after time after time. Okay, the average atomic mass, the mass that is on the periodic table for an element, is the average atomic mass. It accounts for two things. It accounts for the mass of all isotopes. So for carbon, that's the 12, 13, 14. And it accounts for the abundance of those isotopes. Okay, what do we mean by abundance? Isotopes. How abundant that isotope is in nature. How often that isotope is present as opposed to one of the others. Okay, so this number on the periodic table that we use as our mass number right here is the average atomic mass. The units, it's 12.011 AMU, okay? This stands for atomic mass units. Right? We can't use grams. Grams is too big to deal with an atom. All right? So there's a whole unit of itself to deal with these small particles. All right? Okay. Now, you have to know how to calculate that value. All right? You've got to know how to calculate the average atomic mass of an element. Well, let's have a fake one. Let's have X dash 62.10 AMU. Let's have an isotope of X, B. And now it needs to be somewhere close to this value. It's not going to be like way off, right? Give or take 5. We'll make it pretty close. Let's make it 63.99 AMU. And let's have one more isotope. It's not always 3. It can be 2, it can be 5, it could be 10, all right? And let's make this one weigh 63.01, okay? And let's just make up some values for this fake X, element X. And let's say that this isotope here is 90, no, that's kind of big. Let's make him 80.0% abundant, all right? And let's say that this isotope here is 15% abundant. I'm just making these up, guys. But I do know that all of my percentages need to add up to 100. And at this point, they're at 95. So this has to be 5% abundant. Okay, what that means is that, oops, sorry about that, guys. What that means is that 5% of element X in the world is in this form, 80% is in this form, and 15% is in this form, right? So most of element X's atoms are of this form, okay? And then a few are of the other form. And if we were to have our element X, and we would have his atomic number here, and we needed to figure out, well, what is his average atomic mass, we would just need to do something with these numbers, okay? So what I'm going to do, I like that better, is I'm going to take this guy, all right? I'm going to take his mass, and I'm going to multiply his mass times his percent abundance divided by 100 to put it into its decimal form. I'm going to take the next isotope, and I'm going to take his mass, and I'm going to multiply it by the decimal form of his percent abundance, which I get by dividing it by 100. I'm going to take this isotope here, and I'm going to do the same thing. I'm going to take his mass, all of the values, and I'm going to multiply it by his percent abundance in decimal form, which I get by dividing by 100. Okay? And when I do that, make that bigger again, I'm going to get these values over here. So let's go ahead. Oops, let me make that smaller for you guys. And let me get those. So I'm literally just going to go 62.1 times 0.05 equals 3.105. That's AMU. Keep your units. Keep your units. Miss Murphy, you got to keep your units, guys, okay? Times 0.8. Students love to forget about their units. 51.19 atomic mass units for that isotope. And then I'm going to multiply this. I'm going to get 9.45 2 atomic mass units for this isotope. And I just looked up in my calculator. I actually wrote that down wrong. It's 51.19. Is that what I wrote? I'm not sure if that's what I wrote. I'm gonna put my 2 after it. I apologize for that. Now, so remember what we're doing. We are calculating the average atomic mass that is found on the periodic table for our element X, given the masses of the isotopes and their abundances, okay? So we took the mass times abundance divided by 100. Mass times abundance divided by 100. Mass times abundance divided by 100. We ended up with these 3 values. Now, all we're going to do to solve this problem is we're going to add these numbers together, okay? So I'm going to take 3.105 plus 51.192 plus 9.452 equals, and I get 63. I've got 4 sig figs, 4 sig figs, 4 sig figs, 3, 3, and 3, 2. I'm not going to worry about sig figs. Let's make that 3. I just cheated. 63.7 atomic mass units. Now, that's almost it, but there's one more thing I want you to realize. I want you to look at my final answer, okay? First of all, I want you to ask yourself, does it make sense? And the answer is yes, it makes sense. Why? Because my final answer is similar to my isotopes masses. It's got to be in that range, okay? Otherwise, I know I've made a mistake. If I get an answer that's 20 or 40 or 50, I made a mistake mathematically. The other thing I want you to realize is that my final answer is most similar to my most abundant isotope. Isn't this value closest to this value? And isn't this isotope the most abundant isotope? Yes, and it should turn out that way. What that means is that the average atomic mass on the periodic table is most similar to the most abundant isotope. Please notice that even though that this is an average, we never added up and divided by 3. That is not going to give you this answer. So it's a different type of average, okay? Let's finish and let's look at carbon's average atomic mass on the periodic table. It's 12.011. So from that, could we infer which of these carbon isotopes is most abundant? And the answer is yes, yes, because the periodic table gives us an average mass of 12.011, the carbon 12 isotope can be inferred to be the most abundant. Okay? Right on. That's it. I will check you later. Bye.